Hi, this is the SPO600 session for March 27th, 2020. I hope all is well, that you've had a good week and it's been a good start to the online portion of these courses. Obviously, this is continues to be a challenging situation for all of us, and yeah, I hope that things are going well wherever you're settled. So my intention was to have a session on profiling today, and the intention was to prepare you for the next stage of the projects. However, I've become concerned as I've talked with some of you through the week, and I've also looked at the participants table and so forth, that you're not ready for stage 2 yet, because most of you are still working on stage 1. So with that in mind, I want to talk about some aspects of stage 1. I want to sort of review what exactly we're doing with this project, and particularly with stage 1, so that we're sort of all on the same page and we've got an opportunity to get through that stage before we get started with the profiling. So we're going to bump the profiling stuff to Monday. We also have a quiz this Monday, because we have a minimum of 5 quizzes that need to be run through the course. And so we've got 3 in the bag. We've got 2 more that we need to hold. The first of those 2 will be held in this coming Monday. So go to Blackboard on Monday during our regular class time, which is between 11:40 and 1:30. Don't go right at 1:30 because you need enough time to do the quiz. So instructions on how to do that will be sent out in email, but also they'll be in Blackboard, which is where the quiz will be located. And the quiz content will be related to compiler optimizations. So the lecture that I gave on Friday before we took a break for the coronavirus online switch is the material that will be covered by the quiz. The link to that content on the wiki was posted in the email which I sent out today. And you can take that and use that to review. So in particular, what you should know is the names of some of the basic optimizations, things such as hoisting and unrolling and so forth. And you should have a basic sense of how those optimizations work. So if I give you a piece of code, you can look at that code and say, you know, this particular piece of code could benefit from hoisting or something like that. Now remember that these optimizations are things that are performed by the compiler, and normally we don't have to do them. But you need to know what the compiler is doing on your behalf. And I may ask you to show me what the compiler is going to do to the code when it applies a particular optimization. So keep those things in mind. We'll have a quiz on Tuesday. It will be roughly equivalent to what we did in class, which is something that will fit on one side of one sheet of paper. It'll be worth 10 marks, and there will be 20 minutes available to do that quiz. So yeah, pop into Blackboard sometime during our regular class time on Monday. I'll post the video for Monday's class on YouTube, link to it from the schedule, and you'll be able to go to it whenever it's convenient for you. Also, because of the low number of people that have completed stage 1, I'm going to extend the stage 1 deadlines. I can't extend them too far because we do need to finish the course on time, but I'm going to extend them half a week to Wednesday. So if you are still picking your software, or you're having troubles building it, or you're still working on benchmarking it, then you've got a few extra days to deal with that. I've had a number of students that have communicated with me either in the Slack channel, or they've popped in the morning video sessions, or they've sent me email. And the number of students communicating with me has increased through the week. So some of you have sort of put things off as the week, at the start of the week, due to the switch to online and so forth. And I understand that, but really I need you to get working on your stage 1 if you have stalled on that. And as I've said, I'm available. I can assist you in getting through this. So if there are issues with your projects, or questions about your projects, or any issues with accessing the class machines, then by all means let me know. One important reminder with the class machines is that those servers are never backed up. So if you have work that you're doing on the servers, then please make a snapshot of that or a backup copy of it, copy it to a USB drive or to your own machine or to one of the other servers. There is a good chance that one of your fellow students may do something on that server which makes it unavailable. And unfortunately, because the campus is closed, I have only got remote access to reboot and reset some of those machines, not all of them. If I need to go into campus, it will take perhaps several days to do that. So be aware of that, be extra cautious, and make backups of your work and your project data and so forth. Probably best to just copy those between the different machines that we're using for the course. A reminder also that the x86-64 work can be performed on your own machines or on any other machine. It should be done in a Linux environment. So you could do it on, for example, Matrix, or you could do it on a virtual machine on your own system. Do be aware that if you're using something like Matrix, which has quite old tools, you will not be able to install additional tools. So if the tools that you need for your particular piece of software are installed on Matrix, then you're in good shape. But if you need to use tools that are not present on Matrix, then I recommend that you use a different machine. Use one of your own computers or use Xerxes to do the x86-64 work. Since most of us don't have an ARC-64 machine at our fingertips, the ARC-64 work is probably best done on one of the class servers. And I remind you that each of the ARC-64 machines, so that's Archie, Betty, Charlie, and Israel, has different characteristics. So for example, Archie has a large number of cores, but each of those cores has quite a small performance profile. They're basically 24 wimpy cores. Some of the other machines have a smaller number of cores, but they're faster cores. So probably the fastest ARC-64 machine that we have ready access to is Israel. It is a 16-core machine, but those cores are much more performant, much heavier duty cores than we have installed on Archie. There was an issue with Charlie a few days ago. It was down for a while. It's been brought back up now, and you should be able to resume work on that. If you're having any troubles accessing these machines, you need a password reset or you need a key reset or anything like that, please don't hesitate to contact me. So I've had some interesting conversations with folks over the last while, and I want to go back and review some of the details of software building and so forth so that we're all on the same page. So in this course, we've talked about the architecture of computers. And as I've said, there's an entire section on the wiki with several dozen pages that talk about different aspects of computer architecture. The architecture of a particular machine dictates how much data that machine processes at once, how the memory is configured, how the registers are configured, and so forth. Because this varies from architecture to architecture, software written for one architecture may or may not work on other architectures. Over the years, we've become fairly proficient in our industry at writing software that is portable. That is to say, we write the source code once, and then we can build that source code for different types of machines. So most of the software that we have right now in C and C++, most of the open source packages anyways, will build and run across multiple machine architectures. There's also different software architectures and different operating systems. And in some cases, software is written so that it will work with a range of operating systems as well as a range of hardware architectures. So, for example, you've got products such as Firefox, which will build and run on x86-64 machine under Windows, as well as building and running on that same architecture running under Linux. But it can also be used on other architectures, such as Linux and ARC-64. or even Windows and ARC64. So when we talk about portability, in this course, we're primarily talking about portability across architectures, but that phrase, that term portability also applies to software that can be built under multiple architectures. So how do you build a package for different architectures? Well, you take that package and you compile it, giving the compiler the options that are necessary for it to build for a particular architecture. Now, usually, we don't specify the architecture that we want the compiler to output for. So, if you have a piece of software and you build it, normally the compiler will build that for the particular machine on which you're building. In other words, if you're building on x86-64, the software is usually that's produced by the compiler is usually for x86-64. If you build for ARC64 on an ARC64 machine, then by default the compiler is going to produce ARC64 output. It is possible to build on one type of machine for another type of machine. So for example, you could build on an x86-64 machine for an ARC64 machine. But that's not the default. The default is that the compiler will build for the particular machine on which you are building. If you're building on ARC64, it builds for that. If you're building on x86-64, it builds for that. That's called a native build. The alternative is called cross-compilation, and that's where you build on, let's say, x86-64, and you're building the software so that it can run on an ARC64 system. That's not usually what we're going to be doing, so I'm recommending that if you're building for a particular architecture, you connect to and log into a machine of that architecture and build it natively. This is particularly important when some of the build processes actually test the software as soon as it's been built. Obviously, if you are building on x86-64 for the other architecture, then you won't be able to immediately run it, because x86-64 can't run the software that's built for the other type of machine. You have to take it over to the other type of machine and test it over there. So one set of source code can be compiled and produce output for multiple architectures. The easiest way to do that is to take that software over to a machine of the particular architecture that you want to build on or build for, and build it in that environment. So if you want to build for x86-64, take it over to x86-64, Xerxes, your laptop, whatever, build it there. If you want to build it for ARC64, take it to an ARC64 machine and compile it, build it over in that environment. There has been some confusion between input and output. So whenever you're dealing with source files, you're dealing with files that are written in C or in C++ or Haskell or Camel or Fortran or whatever language you want. Those are the human readable versions, and they're treated as the input to the build process. Other inputs to the build process would be things like header files, containing function prototypes and so forth, which are used in some but not all languages. But also things like your make files and so forth. Those are really part of your source code. And as you've seen, that's usually distributed with the source code files. So your input files are your source code files. The original code, as well as the sort of build infrastructure, the scaffolding that's needed to do the processing to build the software for a particular platform. The output of the build process is some code that you can run. We've talked about that as being in ELF files, which is how the binary output is currently stored on Linux systems. I've used the term binary executable, and that seems to have caused confusion for some people. So a binary executable just means a program that is ready to run on a particular architecture, and it includes binary machine code for that architecture. So on a Linux system, that's going to be an ELF file. So when I talk about binary executable, we're referring to a ready to run ELF file in a Linux environment. On a Windows machine, that's going to be a .exe file or a .com file. On other machines, it may have different terminology. It may be stored in a different format. But in all cases, it's a file that consists of executable machine code as well as some control data, some metadata around that allows that code to be executed there. So when I've used the term binary executable, all I'm referring to is code that is compiled, ready to run machine code that you can run on a particular machine. Some environments we call that an executable. Some environments we call that a binary. In some cases that may be called an application or a command or a utility. You can use these terms somewhat interchangeably. They're not exactly 100% compatible in the sense that you could have, presumably, an application that's not a binary executable. It could be a script, it could be something written in Python or compiled into bytecode. But generally speaking, these terms can be used interchangeably. So in order to adapt the build process, in order to change the compiler options and so forth to build for a particular machine, we often have to change the parameters that we use with our tools. So the set of tools that we use, just in terms of terminology, the set of tools that we use to take source code and then compile it, and then do additional processing such as linking, and then finally other stuff such as stripping debug information out of it and so forth. That whole set of tools is called the tool chain. So when I speak of tool chain, not a complex term, it just means that entire set of tools that you need to do that processing. So that will be the C compiler, and as we've discussed in class, the C compiler calls a bunch of other tools in sequence. It will call the C preprocessor, it will do the compilation, it goes through a bunch of optimization phases, producing assembly, and then it calls the assembler, and then it calls the linker. So your tool chain will consist of the C compiler, but the C compiler will depend on all of those other individual tools that will be used to process different parts of the build. But the tool chain is more than that. The tool chain will include things like make or its equivalent, which will sort of orchestrate the individual steps in the process. It may include other tools that do some pre-processing or post-processing of the software. When we're dealing with something really straightforward, we don't need to use make. We can just type in, GCC with a few arguments and compile it. But any sort of complicated piece of code, any piece of code that is more than one source file, or a large quantity of code, or where there's really complicated compiler options that need to be specified, it's really a pain in the neck and almost unviable to do that by hand. And that's why we use these other tools, things such as make. Now, in the old days, make files were written by hand. And if you took the software from one machine to another kind of machine, you had to edit a whole bunch of stuff in the make file. You had to edit which compiler was being used. You had to edit which options you wanted to pass to that compiler. Linker options to specify certain libraries. You had to tell it where files were located, all that kind of thing. And really, this is something that took a lot of time. It would take hours, maybe half a day or a day in some cases, to do all this editing just to build the software for a particular machine. So to solve this, and again, this is review, to solve this, we created various pieces of software. One of the most common is GNU Auto Tools. So the GNU Auto Tools creates some scripts that, when executed, will take a templated make file, a make file that specifies where certain values need to be filled in, which is the makefile.in and the makefile.am. It will take the templated makefile, do some processing on it, and run a bunch of tests on your system to figure out what the correct values are for your particular machine. So which compiler do you have installed? Which libraries do you have installed? What bugs do those libraries have? where the library is present. All of those sorts of questions and adjustments to the makefile are performed by a configure script. Now, why am I reviewing this? It's important to realize that you may sometimes have a package, and that package is designed to work with auto tools, but you will not find a configure script. This is particularly true when you check the package out from a version control repository such as Git or Bazaar or Mercurial or any of those version control systems. It's very common in those cases that the code that's checked in has been set up for use with the GNU Auto Tools, but the processing required to generate the configure script has not been done. In many cases, there's an autosetup.sh file, which is a shell script, or some other piece that when executed will go ahead, perform the steps required to produce that configure file for you, and then you can run that configure file. If you obtain the software as an archive instead of as a repository, you will usually have the configure script present. So you can execute that script with /configure, and it will go and it will build that particular piece of software for you with the options adjusted appropriately for your machine. As you've seen, as we've discussed in class, and as I've demonstrated, you may sometimes run configure and it will come back and say some important piece of the tool chain or a library that is required to build the software is not present. So when that happens, you need to install that particular library or piece of the tool chain, and then you would run /configure again. It will hopefully get past that issue, but it may later in the process discover another library or another part of the tool chain which is not present on your machine. So in that case, it's an iterative process. You need to go back and you need to install these dependencies as you discover them. You may be able to short circuit that process by consulting the documentation. Typically, a file called install, written in all caps, is where the documentation, the notes on what is required to build the software, are held. If that file is not present, then look for other similarly named files. Look for readme.build or readme.install, that type of thing. Now, I've talked about this in terms of the GNU Auto Tools, which produces the configure script. There are alternatives to that. So for example, there's CMake, there's iMake, there's other tools which can be used to produce the correct build scripts and make files for a particular platform. So depending on which piece of software you're working on, you may be able to use a configure script, or you may be encountering other types of build infrastructure. So take a look at the documentation for the particular software that you've selected and find out whether it is built with configure or whether you need to run CMake or other tools in order to prepare for the build. Now, in most cases, the build is actually kicked off with make. And as we discussed in class, make will analyze the dependencies and perform the minimum amount of work that's necessary to build a working copy of the program. So there's a few things to note here. If the build is unsuccessful, then in most cases you can rectify whatever the problem was and you can run make again. Make should analyze the dependencies and it should decide, these are the steps that are required to complete this make. But in the case of a failed make, you may have partial files which can confuse the make process. So if that's the case, and actually as a recommended practice, when make fails, it's strongly recommended that you do a make clean. What that will do is follow instructions in the make file to eliminate any sort of half-built builds. That will mean that you're starting from scratch, and that will guarantee that if you've got a partial file, an incompletely built file, that file doesn't confuse make, and it thinks that part of that step in the build process has been completed when in fact it was not successfully completed. Now, the make file also contains instructions on what options should be passed to the compiler. So we've talked about compile optimization levels. We've talked about, for example, -O0 as being almost no optimizations, not entirely no optimizations, but close to no optimizations. O1 being only the fastest optimizations that can be done just quick and dirty. -O2 being sort of a normal level of optimization where the compiler sort of digs in, spends a little more time optimizing the code to make sure it runs well. And O3 being aggressive optimizations. Optimizations that are usually, but not always, safe to do. So if you're going to use O3, you have to be careful that the software is still working properly when you build it with such aggressive optimizations. As we've talked about, -O fast builds the software to be as fast as possible, even if that means it takes a lot more memory. And -OG builds the software so that it's optimized, but only with optimizations that aren't going to make it really difficult to debug problems with the software. Just to clarify, and this relates back to some conversations that I've had with students this week, those O levels, O0, O1, O2, O3, plus the specialized ones, O fast and OG, and there are some others as well, such as optimized for size. But those O levels merely specify a combination of features. Now the features can be individually specified with -F and a feature name to turn it on, or -F and no dash a feature name to turn it off. So all that's happening when you specify O3 is you're saying, I want to use this preset bundle of features for this particular build. You can start with O3, which selects the bundle of those features, and then you can turn on or off additional features with additional -F flags, as we had previously discussed. Now, question arises, if you're building using a makefile, and the makefile specifies that particular options should be used during the build, then how do you override what's in that makefile and specify a different set of options to be used during the build? Well, there's a couple of ways of doing that. You can specify options to make that will override what's in the makefile. This can be problematic if you've got a complex build that's actually one makefile invokes another makefile and so forth. So a better option is to change the makefiles. Within the makefile, you'll find a number of variables that control the options that are passed to all of the tools in the toolchain. So there will be options that are passed to the C compiler, to the C++ compiler if it's used, to the assembler, to the linker, and so forth. You can go and change those in the makefile and by editing the makefile. However, if you have a complicated build, a complex piece of software, it's quite likely that there is not just one makefile, but there are additional makefiles in subdirectories. So a really complicated project may have dozens and dozens of makefiles in a whole bunch of different subdirectories. Going and editing every one of those makefiles to change the options can be very, very tedious. So, and again, this is review. This is something we talked about in class, but I want to make it really, really clear because you are right now in the process of building your software. It is possible to specify on the configure command line that particular options are supposed to be used. So the most common option or the most common variable for controlling this information in the makefile is ccops, and that's spelled in all caps, CCOPTS. So to run configure and tell it to override the value that's used in the makefiles, you would do something like this. Run your /configure script and specify your ccops as the options that you want to be used for the build. So for example, we could turn on debug and we could specify O3 for a particular build. When you execute this, what will happen is that the make system, sorry, not the make system, the configure system will go and place that particular value of ccops in all of the make files. However, if the build requires other options in addition to this in order to build successfully, then you may have broken the build by configuring it in this way. So what you should do is you should run just configure without any particular options first. Go look at the make file and see what the value of ccops is. So take that value that configure has specified when run with no options, and then change that. Rerun configure with the options that you want, taking into account any particular ones that that particular piece of software needs. So for example, if a particular piece of software requires a feature called foo, so the ccops in the make file may say something like -02-f foo. If you are altering the ccops, what you could do is you could run configure, specify ccops equals, and then quote the options that you want, but be sure to include that -f foo in that group of options that you're going to pass into the configure script. Configure also allows you to specify things like the prefix. And the prefix is just the directory in which everything related to the software will be stored. Historically, that's often been /user. What that means is that libraries that are produced by the build will be installed into /user/lib, and the binaries are installed into /user/bin, and so forth. Another very common prefix to use is /usr. For example, /usr/local. So you could, for example, specify a prefix of /usr/local, and then the binaries are going to go into /usr/local/bin. The libraries are going to go into /usr/local/lib, and so forth. Now, if you are using the default prefix and you build the software successfully, when you try to do, as a regular user, a make install, that software will not install because the system will try to place the files in directories that are not writable by regular users. This is not a bug, this is a feature. This is preventing you from wiping out the existing working copy of that software. So for example, if you are changing gzip and you try to do a make install, it will wipe out the system's already installed copy of gzip and replace it with the one that you've just built. Now, if the one you've just built works fine, then all's well. But if the one that you've built is an older version or a newer version, it may cause some stuff on the system to break. Also, if the version that you've built for some reason is incomplete or it doesn't work 100%, then you may have broken the system and the machine may not work properly, or maybe erratically, or perhaps the next time you try to start it up, it won't boot properly. So don't install software onto the system files. The best way, the easiest way to make sure that you do not do that is to never ever run any part of the build process, and especially never run make install as the root user. So normally you would execute stuff as the root user using the sudo command. So don't do a sudo make install, just do a make install by itself. Now, if you want to install the software and to test it, but you don't want to wipe out the system's copy, then you need to specify a different prefix so that the software installs into your choice of location instead of the location that it would normally install to, which is where the system software is right now. You would do this by using configure with the prefix option. So here's an example of how that would be done. And let me switch over to the screen. You could do something like configure. And then here you could specify your home directory. Whatever your name is, you put it there. Or you could specify a subdirectory. Whatever directory name you want to use. And you can combine this with the CCOps option that I showed you a moment ago if you want to build with custom options and you also want to place it in a particular location. So by adding extra options to the configure script, you can specify that the configure script should place additional specific options into the make files that it creates. Now, the make system is capable of detecting when a source file changes. And we talked about this in class. If you change 1 out of 1,000 source files that might exist in a project, and then you run make again, it will build only the minimum amount of stuff that is affected by the change to the source file that you just made. However, make is not usually aware of changes that have been made to the make file itself. Meaning that if you change the CCOps within the make file and you run make again, it will often decide that there's nothing that needs to be done because the software has been built since the source code was last changed. It doesn't take into account that the software has not been built since the make file was last changed. Therefore, if you have rerun configure or if you have manually edited the make files, it's important that you run make clean. That will wipe out the previous build so that when you run make again, it will go through and it will create an entirely new build, taking into account the changes that you have made. It's also important to realize that this is also true when you take the software from one machine to another. So for example, if you have a version of the software where you've maybe configured it in a particular way, and then you take that software from, let's say, Xerxes over to Israel, and you build it on that other machine, which is of a different architecture. First off, it'll look at the timestamps, and it may look at those timestamps and say, I don't need to do anything because the software has been built recently and it's all set to go. The make system won't realize that you have moved the software to a different architecture. And so it will think that the code which was compiled on the old machine, which was a completely different kind of machine, is up to date. Therefore, when you try to run that software, it won't work. The other thing is that even if you do a make clean and then you build the software, you haven't run configure on the particular target machine that you want to run it on. For that reason, there's a bunch of assumptions that configure may have written into the make files that is relevant only to the other machine. So if you take the software from one machine to another, all the source code and so forth, you need to run the configure script again, and then you need to run a make clean and a make to build the software fresh for the new architecture. I mention this because this is something that has tripped up a number of students in past semesters as well as in the current semester. So these are steps that are required to build the software. Once you've built the software, you need to try it out. And most, but not all software that is distributed as source code may contain instructions within the make file that does a self-check. This is not usually a deep sort of performance check. It's just a sort of a smoke test to make sure that the software works the way that it's supposed to work. Now, the complexity and the level of detail in those tests varies considerably from one package to another. So for some packages, you might run the tests, and that's typically done by running either make check or make test. It may do just a very quick half dozen tests to make sure the software sort of looks like it should run fine. If you grab another piece of software, it may have a much more comprehensive set of tests, and ideally, that's a kind of nice thing to have because it gives you a greater assurance that the software has built successfully. Some software has hundreds of tests. Some software has hundreds of thousands of tests. Browsers, for example, and Office suites typically have hundreds of thousands of tests. And the amount of time it takes to do those tests is actually far in excess of the time it takes to actually build the software in the first place. So it might take 20 minutes, 30 minutes, something like that to build the software. And then it may take hours and hours. I've seen test suites that take more than 12 hours to run successfully. So you may want to do that just to prove that your test has worked fine on a particular machine. But those tests may also be useful to you in that you might be able to do your benchmarking by taking one or two of those tests and expanding them. So they do the same test, but they use a larger piece of data. I say a larger piece of data because most tests are designed to run quickly. They're designed to prove that the software is working. They're not designed to really stress test it. With benchmarking, you want to stress test the software because if it's something, if your benchmark test takes a fraction of a second, it's hard to get accurate time, and it's hard to check repeatability because that fraction of a second could be when a network packet came in or when a keystroke came in, and that can throw your results off considerably. So going back to the basics here, you're going to run configure, or what the equivalent is for your particular piece of software. You're going to use make to build it. Then in many cases, you could run a make check or a make test to verify that software. Once you've got to that point, once you've got the software and you're confident that it's working on your machine, that's when you need to do the benchmarks that we've talked about, which is testing the performance of the software. Now, a reminder again, because I'm seeing people picking software projects that are not resource intensive, they don't really make the machine work hard. If the machine's doing hardly any work to run the software, then speeding up that software is not going to make much difference. So particularly if you've got software that's waiting for the network or waiting for the user or waiting for storage, then you can speed up that software all you want, and it's not going to go any faster because the performance of that software is not really limited by how much work the computer's doing or how fast it's getting the job done. It's limited by other external factors. So bear that in mind, and I'm repeating it just because I'm seeing people selecting packages, software that is not CPU intensive, and there is value in optimizing that. People spend a lot of time optimizing stuff so that it uses less battery and so forth, but that's much more difficult to check. So be sure that you pick software that makes the machine work hard, software that really sort of taxes the machine and takes a while to run. So I hope this has been useful as you're going about the build process. There's been some additional questions about what exactly I'm asking you to do in this first piece. So let me just recap that. And again, this is review both from last Monday's session and from previous conversation, but I want to make sure that everybody's on the same page here. So what you want to do is find a piece of software, grab that software either as an archive, which is a tarball, or a zip file or something like that, or clone the repository in which it is stored from Git or Mercurial or Bazaar, what have you. Take that software, put it on two machines. One of those machines, x86, either your own or Xerxes. The other machine, one of the ARC64 machines, could be a Raspberry Pi, but it's probably easier to use one of the class servers, Archie, Betty, Charlie, or Israel. Put the software there, build it there, check that it works, and then test it. Make sure that you keep the files that you tested it with. So you're going to create some meaty enough files of the right type that your software will take at least a few minutes to run. If it takes an exceptionally long amount of time to run, then check for things like that the machine you're trying to run it on has enough memory to do that well. There was a conversation earlier today about a machine that may not have had enough memory to run a particular test. And so verify the memory that's available. Just as a refresher, if you want to see the memory picture on a machine, use the free command. It will show you how much RAM is installed, how much of that RAM is in use, and how much is available. If you want to see the CPU capabilities of the machine, there's a file called CPU info, which is in the proc directory. So you can view that file with a command something like this. So on this particular machine, we can see, for example, that there are multiple cores. And on this machine, it's going to report that there are 16 cores. That's not strictly, oh, sorry, it's reporting only 8. Okay. Now, depending on how this machine's configured, it may report the number of physical cores you've got, or it may report the physical cores plus the hyper-threaded cores. On Intel machines, it may often report twice the number of actual cores that are installed because of hyper-threading, and that sort of distorts the picture a little bit. On some other machines, so let's, for example, go over here to Israel. And if we do take a look at proc CPU info over here, we'll see a more concise description of each core. And I'll scroll through this. You see that it's reporting 16 cores numbered 0 through 15. You may find some machines in which it reports an asymmetrical group of cores. So for example, if I were to run this on my Chromebook, I would see that there are 4 cores of one type and 2 cores of another type installed on that machine. That's called a big little architecture. It's common on mobile machines. The low performance cores are used to save energy. So when the machine's not doing too much, it's just running a few things in the background, it'll use the low energy cores. And when it needs high performance, it will fire up the sort of energy hungry, high performance CPU cores in order to get stuff done more quickly. So those are a couple of commands you can use, free from memory. Do a less of /proc/CPU info to find details about that. If you want a more complete overview of what's installed on each machine, you can use the lshw command. That should be installed on most of our machines, but if it's not, then you can install it. As I've said before, to install software, use the sudo command, followed by either dnf or yum or apt, depending on the operating system which is installed on that machine. And then finally, the name of the package. So as an example, if you're on a Fedora machine and you want to install lshw, which stands for list hardware, you would do something like sudo dnf install lshw. If you wanted to do that on an Ubuntu machine, such as Israel, it's a very similar command. It would be sudo apt install lshw. And the difference there is that the different flavors of Linux use different package managers. DNF is used on systems such as Fedora. Yum is an older one that is used on older versions of Fedora, as well as CentOS and Red Hat Enterprise Linux. And apt is a package manager that's used on Debian and Ubuntu systems. There's some others out there as well. For example, there's one called Zypper, spelled with a Y, which is used on OpenSUSE systems, but none of the class servers are OpenSUSE systems. So you can use that to get information about the system. If you follow the steps that I've outlined here, you should have a fairly simple build process. You may need to install a few libraries depending on your software, but you should be able to go through that build process. If you get stuck, read your error messages carefully. And I always tell people to read the error messages from the bottom up. So the last line of your error messages will usually give you a summary of what went wrong, but you may need to read up higher in the error messages to get the cause of that error that's reported at the end. So read backwards, go up until you find something that gives you the actual detail of what went wrong during the build. It may be a source code issue, it may be a library issue, it may be something like running out of memory for the build process, but do go ahead and read backwards through your error messages until you find what's going wrong. Now, with all of this, if you have any questions about your build, and I realize that this may be foreign territory for some of you, most of you probably, if you've got an error message that you're having troubles decoding, or if you are on a step and you're not sure what to do with that, then get in touch with me. So in all of these things, there's 3 ways to get in touch with me. I've put them in the email that I sent to you. One of the best ways is to pop into the video session. So that's whereby.com/ctyler, as written in the email. And I'm there each morning between 9 and 10 a.m. Don't randomly pop into that channel at other times because I may be using that channel for other discussions. But any day between 9 and 10. If for some reason that doesn't work, you've got classes from 9 to 10, or you need to meet at another time, then please do not hesitate to send me an email and request another time, and we'll set that up. If it's inconvenient for you to do this by video, or that you prefer not to do it by a video and audio chat, then please feel free to use the Slack channel. Slack is a chat tool that's used by a lot of software development teams. You can access the Slack channel from the communication tools page on the wiki. There's instructions there on how to get to that Slack channel. Be aware that I do monitor Slack every weekday because it's what I use to communicate with my own development team that are doing software development for applied research. I don't check the class Slack channel that frequently, so it might take a little while before I can get back to you. So if you're going to be doing some work, you can just leave Slack open in the corner, and I'll get back to you as soon as I notice that you've got a message there. The third way that you can get in contact with me easily right now is by sending an email. I try to respond to emails the same day. Weekends are weekends, so I may not respond as quickly on the weekend. But there's 3 approaches there. Use any of them or all of them to get in touch with me as you see fit. Now, it's important that where possible, you give me the background to the question at hand. So give me a screenshot or some screen snippets with an error message. Better yet, cut and paste the error message, stick it in your email. But give me the context. Tell me what machine you were on, what you were trying to do, and remind me of which piece of software you're dealing with. I can probably, in most cases, grab that same piece of software and do a quick test here to see if I can find the same kinds of problems that you're experiencing. Or we could do a collaborative session. We can screen share over the video link or something like that. And of course, I can log into the machines that, the class machines that you may be working on. So do take advantage of these different ways of getting in touch. Don't hesitate to reach out to me if there's an issue that you've encountered, and I can work together with you on it. That said, I'm not going to do your project for you, so use that, give it a fair shot yourself. But whenever you run into something that's blocking you, don't get stuck there and spin your wheels for hours or days at a time. Don't hesitate to reach out, and I'll take a look. As well, don't hesitate to use other students as a resource. I would encourage you to cross-contribute to each other's projects. So by email or by Slack channel, you can ping each other. Slack actually has audio conferencing as well, so you can use that to chat as you're working on stuff, and do help each other out, and feel free to do that. That's not in any way cheating. I do request that if you've got help from someone else, or you've got some ideas from someone else, mention that in your blog. That's only fair and respectful. So hopefully this clarifies some issues that may have existed around the project. Hopefully it gives you enough information that you can proceed successfully with the stage 1 work. I've been a little alarmed to see how few students have chosen a project and written it on the participants page. So if you've picked a project and you've just forgotten to do that, go to the participants page and fill in the columns so that we know which piece of software you're working on. As a reminder, this is not group work. I don't want multiple students working on the same aspect of the same project. However, some of these projects are huge, and some of the software pieces that we're working with are huge, and there's no reason why several students can't work on different parts of the same piece of software. So for example, there's an audio package called SOX, S-O-X. It's great in terms of being well-written open source. It has lots of capability, and it really does use the CPU hard, depending on what you're doing with it. It's kind of a Swiss Army knife of audio processing. It can change files from one format to another. You can change stereo to mono or 7.1 multi-channel sound into stereo, all sorts of things like that. If there's several students that are working on SOX, I would expect that you work in different parts of it. But that project's big enough that that's easy to do. So one of you could take a look at the echo function. It's an effect that you can add to sound to make an echo. Another one could work on a normalization function or a clipping function or any one of a number of other functions that software provides. If you take a look at the effects that SOX can add to audio, there's dozens and dozens and dozens of them. There's no reason at all why, if we wanted to, the entire class could work on different aspects of that same piece of software. And the same is true of other things. So for example, compression software, there may be different parts of the code that are used to compress different types of data. You may have, as an example, you may have one compression program that uses one approach for compressing text. It may use a different strategy for compressing graphics, and it may use yet another strategy for compressing database data or something like that. And so again, it's entirely reasonable for 2 or 3 students to work on different aspects of that. And so you could help each other along, but each of you needs to be working on a separate aspect of that in a separate function, separate piece of the code. But again, these projects are large enough that there's plenty of pieces of code within one project, and that's fine. So yeah, take a look at the participants page, coordinate with other students if there's several of you that are working on the same project to make sure you're not stepping on each other's toes. But feel free to proceed like that. So yeah, with that, we're slowing down the pace a little bit in order to make sure that we get project one done. I'm going to pivot and start talking about the profiling on Monday. We're going to use a couple of different tools, and the point of a profiling tool is to tell you where the CPU resources are being used within a program. It's typical that you've got a handful of functions that do most of the heavy lifting for a particular program. And those are the ones that if we're going to speed up the program, we need to focus on. Take a look at where that program is spending 60, 80, 90, 99% of its time. So what we'll take a look at in the next piece is how to do profiling, how to analyze software to figure out the hot functions, we call them, the functions where most of the time is being spent. Again, we're focusing on optimization for CPU, but this usually is tied in with other types of resources like energy consumption. If you make the CPU spend less time on a particular task, it's definitely going to spend less energy on that as well. Okay, I hope that provides the information that is needed to nail this stage 1 of the process. There's those 3 ways that you can get in touch with me, and I hope that you're not shy about doing that. Feel free to use whichever of those approaches works best for you. And again, I'll do whatever I can do to help you get through the rest of this course and through these projects, even though things are a little bit more complicated because of the online format. So I'm going to stop there. Monday we will do the quiz, and I'll talk to you about profiling. Any questions you have, send them to me in one of those 3 ways, and we'll look forward to resuming this stuff next week. I hope that you stay safe, stay healthy, and have a fantastic weekend. You keep your distance from other people. I would hate to hear of any of you getting sick or critically ill with this COVID-19, but as much as possible, enjoy this time, and look forward to touching base with you all on Monday. Thanks.